Today's date is May 31st, 2009. In a matter of hours, Air France Flight 447, a scheduled commercial operation between Rio de Janeiro and Paris Charles de Gaulle, will depart the South American metropolis. On board will be 12 crew and 216 passengers. This evening's flight will be operated by an Airbus A330-200 series aircraft, a medium to long-haul wide-body manufactured in Europe by Airbus Industries. Of the 12 crew, Captain Marc Dubois will be in command, the remainder of his augmented cockpit crew, comprising of First Officer Pierre-Cédric Bonin and David Robert. Sadly, Air France 447 will never reach its destination. Approximately 3 hours and 40 minutes into the flight, an environmental event will trigger a chain reaction, which ultimately will result in the loss of the aircraft and all those on board. As the following hours and days unfold, the despair and devastation of tonight's events will not only impact heavily on the family and friends of all those on board, but as an industry, aviation itself will be plunged into a period of profound reflection, culminating in what will eventually be a protracted examination of what we know and what we take for granted regarding pilot training and the man-machine interface. In truth, this evening's events will come to reshape aviation as we currently understand it, and profoundly change the landscape for all interested parties, the airlines and those who fly for them, the manufacturers and the aircraft they design and build, the flight schools and all those who graduate from them, and the regulators, the custodians of all that is safe and acceptable in aviation. Tonight will be the start of a long process whereby we come to re-evaluate our understanding of the handling characteristics of large transport aircraft, particularly in the context of flight at high altitude. It will be the start of a process whereby we not only question what our pilots know, but also the very fundamentals of how we actually teach them. Hopefully this video will provoke those in society who've been so quick to judge, ridicule and jump to conclusion. It is not an effort to exonerate, but it is unapologetically an effort to highlight what desperate humans in desperate situations can do, an affirmation of the fact that we are all human, and in that fact alone hides our greatest strength as well as our greatest weakness. This is the story of what really happened to Air France Flight 447. Sunset this evening in Rio will be at 5:17, and at these latitudes twilight is brief. So it will be that almost 3 hours later, Air France 447 will push into the darkness to commence its near 11-hour journey back home to Paris. Considering the length of the flight ahead, the aircraft will be heavy, with an estimated takeoff weight of just under 233,000 kilos, just over 70,000 kilos of which will be fuel. At 20:29 local, or 22:29 UTC, the crew of Air France 447 will release its brakes, advance the thrust levers, and begin its takeoff roll. Anticipating an en route climb to the northeast, the lights of Rio will fade into the distance behind. As is customary on such a long flight, some time will pass before the in-flight service will commence. However, in light of the long night ahead, the cabin crew will be mindful of most passengers' desire to settle down reasonably early, in an effort to get some rest and hopefully some sleep. Amongst the crew there will be much discussion on how each has passed the time in Rio, who's gone where, seen what, and most importantly, what has been bought. Anticipating some time off after arrival back in Paris, some will already have started planning their next trip. In the cockpit, Captain Dubois will occupy the left-hand seat. Age 58, his aviation career has stretched over 11,000 hours, just over 6,000 of that as commander, with 1,700 hours of that being command time on the A330. The right-hand seat will be occupied by First Officer Pierre-Cédric Bonin, age 32, and the nominated handling pilot for this evening's leg to Paris. With 3,000 total flight hours, 800 of which is on the A330, Bonin is the least experienced of the flight deck crew. Fulfilling the three-man complement will be First Officer David Robert, Having been the handling pilot for the outbound leg a number of days beforehand, he will now perform the duties of the relief pilot for the return leg. Aged 37, he has a total of 6,500 hours, of which nearly 4,500 are on the A330 type. Two hours 25 minutes after departure from Rio, 447 will leave the northeastern coastline of Brazil, close to the city of Natal, as it prepares to enter oceanic airspace. Unlike the previous construction of domestic airspace, transit over the ocean is largely completed procedurally. What this means is that once beyond the range of land-based radar stations, the aircraft will have to make routine position reports itself, either electronically or, in the absence of such a service, by pilot voice communications over HF radio. Indeed, as 447 leaves the coastline at Natal, the station located on the island of Fernando de Noronha will provide final radar coverage out as far as the Salpu intersection, which the aircraft is expected to reach in approximately 50 minutes at 0145 Zulu, 3 hours and 16 minutes after departure, and a mere 29 minutes before the accident. Off the Brazilian coast, the airspace through which the flight is planned to transit is divided into various blocks called FIRs, or Flight Information Regions, each with its own controlling agency. Between waypoints Natal and Tassel, flights remain under the control of Brazilian Air Traffic Control, through the respective controlling agencies of Recife and Atlântico. Beyond Tassel, Brazilian agencies relinquish control over flights on the route, as aircraft enter the Dakar FIR, where Senegalese authorities monitor flight progress over a large area of the southern mid-Atlantic. Up until this point, the flight has been uneventful, with the aircraft now cruising at flight level 350 or 35,000 feet. In communication with Recife Control, the crew will be issued HF radio frequencies for the next controlling agency, namely Atlântico, and further instructed to contact them when the flight reaches the Intal intersection. At 0131 Zulu, just prior to Intal, the Recife controller will issue new HF frequencies for Atlântico, and additionally a frequency for Dakar, with instructions to make a voice call to Dakar no earlier than the Tassel intersection. At 0133 Zulu, the crew will attempt an ADS, Automatic Dependent Surveillance log-on with Dakar Oceanic Control. This is the electronic, satellite-delivered digital communication and tracking system mentioned earlier. It is the current industry best practice with regard to the execution of oceanic procedures, and works on the principle of a monitoring contract being triggered by the aircraft with a controlling agency prior to crossing their FIR boundary. With the aircraft having reached out for this service, the controlling agency for its part will reply in turn, notifying that they have effectively accepted the aircraft's initial handshake. Although this handshake, per se, must be physically initiated by the crew, once the controlling agency have accepted oversight of the flight, everything from that moment on happens automatically without further crew involvement. Indeed, with this initial contact having been made by the crew, handoff at the appropriate time between one controlling agency and the next is likewise usually an automatic feature conducted between the agencies themselves, with the final agency in line usually logging the aircraft off once it comes time to finally terminate the service. Like most things in life, the service is not free, with the controlling agency charging the respective airlines for the privilege. That being the case, specific data relating to the aircraft and flight in question must be preloaded into the system. After all, it's quite difficult to get paid if you don't know where to send the invoice. This pre-populated information should be uploaded with the initial filing of the flight plan. As luck would have it this evening, due to a simple typo issue when filing the flight plan, the data upload will not allow for correct identification of the flight, and as such, despite the crew's best efforts, an ADS connection will not be established with Dakar Oceanic. The inability to log on will have another implication. Thought of as going hand in hand with the ADS connection is a CPDLC connection with the same agency. CPDLC, or Controller Pilot Data Link Communications, is essentially a glorified text messaging system enabled between the pilots and the controller, who may be located many thousands of miles away from each other. Facilitated through a satellite linkage, it allows the pilots and controllers to interact with regard routine operational issues such as flight level change, route amendments, etc., without the need to communicate directly by voice. As the ADS-CPDLC combination allows for almost real-time monitoring and communications, not having the facility is inconvenient to say the least, but it's certainly not a showstopper. HF radio communication predates all this technology, and so, in the event of its non-availability, the good old radio once again becomes the fallback. There's good reason, however, why technology developed in this direction in the first instance. HF communication is not an experience that most pilots warm to. Transmissions are often negatively impacted by atmospheric interference, noisy and congested, to the extent that it can take multiple attempts and quite some time to get a word in, make a request, or report one's position. Such being the norm, continuous monitoring of the assigned HF frequency becomes irritating at best and nigh on impossible at worst. As a result, on first contact with the controlling agency, the crew will request a cell call or selective call check. Once establishing that the cell call system is operational, the controller, when wishing to communicate with a specific flight, will transmit a unique 4-letter code specific to that aircraft. The onboard HF radio receiving this code will trigger an audible alert to the crew, indicating the requirement for them to call back the controller, thus avoiding the need to continuously monitor the assigned frequency. At 0134 Zulu, the crew will contact Atlantico Oceanic and successfully complete a cell call check. This will be the last voice communication with Air France 447. With communications established with Atlantico Oceanic, the aircraft will continue to follow its filed route via Salpu, Oraro, and Tassel intersections. At these latitudes and just ahead, the filed routing will take the aircraft through the ITCZ, or the Intertropical Convergence Zone, a band of weather which circles the globe fueled by global circulation patterns. This evening's en route weather is not abnormal or uncharacteristic, and some activity in the ITCZ region is anticipated. If we overlay the convective activity ahead of the aircraft, a clearer picture of the environment ahead begins to emerge. This image was generated from photographs taken at 0200 Zulu on the morning of June 1st, approximately 15 minutes before the accident, by the Meteosat 9 satellite positioned over West Africa on the 0 degree or Greenwich meridian. The satellite photos clearly show an active meteoscale convective system across the flight path, with cloud tops between 35,000 and 55,000 feet. About 90% of the cloud material seen on images are actually multiple layers of convective debris fields from dying storms and activity that occurred previously during the day, with extensive cirrus fields at higher levels. The active thunderstorm areas are actually defined not by the bright colours, but by small-scale mottled areas of cold cloud tops, displayed here in grey and white. This is the heart of the storm. Temperature trends suggest the entire system was at peak intensity, developing rapidly between 2300 and 0100 Zulu, and finally dissipating many hours later around dawn. From a turbulence perspective, the cold spots described above, i.e. those areas of grey and white, would be the areas of highest concern, as they signal the location of an active updraft producing new cloud material in the upper troposphere. Coincidentally, at 0200 Zulu, Captain Dubois will leave the cockpit to commence his rest period. From post-accident modelling, it will be determined that 447 flew through the top of a storm positioned adjacent waypoint Salpu, and subsequently into the heart of the following storm in the vicinity of Oraro. As the aircraft enters the first of weather at 0145 Zulu, 3 hours and 16 minutes into the flight, and approximately 29 minutes before an impact with the sea below, the crew will discuss the possibility of climbing to flight level 370 in order to try and get above the weather they are experiencing. However, reviewing their performance data reveals that any further climb given their weight will not be possible. At approximately the same time, First Officer Bonan will dim the cockpit lights and turn on the landing lights buried in the wing root to better see conditions outside. His words will be few, but importantly acknowledge that the aircraft has now entered weather. It looks like we're entering cloud cover. It would have been good to climb now, huh? As the aircraft reaches the Salpo intersection, radar service will be terminated. From here on, the aircraft will be out of sight until it re-emerges from the oceanic portion of its voyage, somewhere along the African west coast. Shortly after, Bonan will remark, "I don't have the impression there was much storm." Captain Dubois, for his part, will simply reply, "It's going to be turbulent for my rest." In preparation for his rest, Dubois will ask Bonan if he will be doing the landing into Paris, to which he would simply reply, "Yeah." This fact from an Air France procedural perspective is important. As being nominated the pilot flying from the right-hand seat, it is he who will be designated the pilot in command in the captain's absence, despite the fact that of all three crew members, he is the least experienced. Subsequently, much will be made of this fact, but the reality in most augmented crews like this across the industry, qualification to act as the relief commander is based on merit and only follows on the back of rigorous training and successful completion of the associated line check. So, despite the experience issue raised, nothing suggests that Bonan was unqualified to fulfill the role, although the later accident report will question the level of support and quality of training Air France as an operator provides its first officers in anticipation of such an undertaking. As Robert returns from his rest break, where he has been for the last 3 hours, Captain Dubois will leave for his. He will provide no specific briefing to Robert on the flight's progress to date, other than to confirm the HF radio frequencies for Dakar, the next controlling agency, whose FIR they will shortly enter. Robert will assume his position in the vacant left-hand seat, and as Dubois leaves, it is Bonan who quickly fills Robert in on the aircraft's current inability to climb above the weather, and that they could expect some further turbulence, similar in intensity to that which they had experienced moments earlier. With Dubois having left the cockpit, Bonan and Robert will be left alone at the controls of the 330. Some 90 minutes beforehand, 447 will have received information from its Operation Control Centre in Paris about the presence of a convective zone linked to the intertropical convergence zone between Salpo and Tassel. In retrospect, however, nothing suggests that Robert was made aware of this fact as he assumed his place on the flight deck. At 02, 06 and 5 seconds, 4 minutes before the autopilot disconnection, Bonan will call the cabin crew and advise them of possible turbulence up ahead. In 2 minutes there, we ought to be in an area where it might start moving around a bit now and then. You'll have to watch out. Despite the warning, Bonan will express no intention to deviate from their current course. 2 minutes later, Robert will adjust the gain or sensitivity of the onboard weather radar, a common practice amongst pilots, which will often significantly increase the displayed weather on the screen, both in quantity and intensity. Parts of the storm will be depicted which most probably were not visible beforehand. Reacting to what will be displayed, he would suggest to Bonan that a change in course would prove prudent. Do you maybe want to go to the left a bit? You can possibly go a bit to the left. I agree we're not in manual now. Well, as you can see at 20 with then it's me who just changed it to max, explaining his adjustment of the radar controls and the apparent increased intensity of the displayed weather. Bonan will comply and subsequently make a modest 12-degree course change to the left. At 028 and 17 seconds, there will be a noticeable change in background noise perceptible on the cockpit voice recorder of precipitation striking the aircraft. Bonan will comment on the perceived change in cabin temperature and his awareness of a sudden smell on the flight deck. Did you do something to the AC? Followed by a query, what's that smell? Robert, having more experience of transiting the ITCZ, will identify it immediately. It's ozone, that's it, we're all right. As the turbulence intensifies, they will attempt to slow the aircraft from decimal 82 Mach to 0.80 in order to improve manoeuvrability margins in the rough air, and engine anti-ice will be selected on. Unbeknownst to either Bonan or Robert, Events are about to change for the worst. Within seconds, the pitot probes will be overwhelmed by the ice pellets through which they are flying, setting in motion a cruel and devastating chain of events, which will, within a short 4 minutes, see 447 heading to the bottom of the Atlantic Ocean. Why the crew of 447 will proceed straight ahead into the worst of the weather will never be known for sure. Some have suggested that a possible attenuation effect or blanking from the Salpu storm may have somehow hidden from view the convective build-ups around Oraro, or at least may have significantly masked their level of intensity until such time it was too late for the crew to avoid them. Other traces of aircraft transiting the area this evening will show very different courses of action. Traffic on the adjacent track to the west proceeding to the Decon intersection, indicated in beige, will make obvious efforts to deviate around the westernmost extremity of the storm. Likewise, Air France 459, just over 35 minutes behind on the very same routing, outbound from Sao Paulo, also en route to de Gaulle, will likewise make deliberate efforts to not only circumnavigate the Salpu storm, but also the convective activity around Oraro, by subsequently deviating significantly east of the filed routing. The details of what happens next in the story of 447 are complex. Unlike other presentations on the subject, the objective here will be to give the viewer an in-depth understanding of Airbus design philosophy and a deeper understanding of how the relevant systems on the 330 actually work. In doing so, the hope is that you'll be better placed to understand what the pilots did, how the aircraft behaved, and why at times the interaction between both was less than efficient and ideal. The finer points of our excellent investigation can often prove difficult to comprehend, and without this comprehension, the true story behind the facts can remain elusive and frustrating. Stay with me over the next while as they explain the concept behind Airbus's design philosophy and lift the lid on some of the vital aircraft systems and aerodynamic principles which play a significant part in the story of Air France 447. Fly-by-wire and pilot side-stick logic, flight directors, why we use them and how they operate, flight control laws and their reconfiguration, ECAM, the means by which the 330 communicates failure information to its pilots, and the intricacies of the pitot system around which the whole event hinges. And finally, the aerodynamic stall itself. What causes it? How is it identified? And how, if unfortunate enough to find ourselves in one, do we recover? Armed with this information, the complexity of what will be presented in episode 2 of this story will, I hope, be a little bit more comprehensible. The accident aircraft shown here, registration Golf Zulu Charlie Papa, is a 330-200 series aircraft, retailing at a whopping $238.5 million US. The 330-200 type first flew in 1998, having been predated by its sister, the A330-300, in November 92. A direct technological descendant of the A300, 310 and 320 aircraft before it. At its introduction into service, the A330 represent the pinnacle of Airbus fly-by-wire research and development. Fly-by-wire is a system that replaces the conventional manual flight controls of an aircraft with an electronic interface. The pilot's actions in the cockpit are converted into electronic signals transmitted by wires, hence the fly-by-wire term, to flight control computers, of which the 330 has 5, each controlled by a guarded switch on the overhead panel. The purpose of the computers is to determine how to move the actuators at each control surface to provide the ordered response. With a 330 design, flight control computer failure is supported by shifting the failed unit's responsibilities onto the remaining computers, thereby utilising a non-mechanical backup system, with the one exception of the rudder. As the pilot now generates an electric signal to be interpreted by the flight control computers, there is in fact no physical need for the traditional large yoke most commonly seen in earlier conventional aircraft. Instead, Airbus have replaced the traditional yoke with a side stick, located adjacent but forward of each pilot's seat. Fully fly-by-wire systems interpret the pilot's control inputs as a desired outcome and calculate the control surface positions required to achieve that outcome. This results in various combinations of rudder, elevator, aileron flap and engine controls in different situations using a closed feedback loop. The pilot may not be fully aware of all the control outputs acting to affect the outcome, only that the aircraft is reacting as expected. In effect, the pilot through the side stick tells the aircraft what to do, without being concerned how this is actually being achieved. The fly-by-wire computers act to stabilise the aircraft and adjust the flying characteristics without the pilot's involvement, and to prevent the pilot operating outside of the aircraft's safe performance envelope. In other words, Airbus's fly-by-wire philosophy takes advantage of a system's ability to limit pilot demand so as to not allow deliberate acts which would prove detrimental to safe operation, for example a stall, overspeed or overbank. Much has been made of the different manufacturers' approach to fly-by-wire philosophies. Some naysayers describe the protections which the system can provide as the pilot wanting something and the computer deciding if they will actually allow it. This implies that the pilot always knows best, should always be obeyed, and should be left with the final authority as to whether it's appropriate or not to bring the aircraft deliberately outside the normal flight envelope. In truth, there's no reasonable scenario I can think of where a large transport aircraft should be deliberately rolled, looped, stalled, or significantly oversped. On the contrary, however, aviation history is littered with accident reports of aircraft which have inadvertently exceeded certain design parameters, with all too unpleasant an outcome. The protections are there for good reason, and in my own personal experience I've had to rely on them at least once in my career and was very grateful to be able to do so. Each side stick is lightly spring-loaded to the centre position and is equipped with a red combination autopilot disconnect and takeover push button, which is conveniently positioned under the pilot's thumb. On the front, forward-facing side, again conveniently placed for the pilot's grip, is the push-to-talk communication trigger. The two side sticks are not mechanically linked, nor do they move unless the pilot actually moves them. Moving one does not move the other, and other than to check physical serviceability of the input command, the relative displacement of the side stick from neutral is not displayed to the pilot unless the aircraft is on the ground, with at least one engine operating and hydraulic power available. With engagement of the autopilot, the side stick is physically locked in the neutral position, and although not a recommended procedure for autopilot disengagement, a reasonably modest amount of physically applied pressure will break the latch and return the aircraft to direct pilot control. From either pilot's seat, looking across the cockpit does not afford a very clear visual picture of what the other pilot may or may not be doing with his side stick. Of huge importance and emphasised to new Airbus pilots from day one is the fact that each side stick should be operated in isolation, never in unison. If both side sticks are moved at the same time, their inputs are summed. For example, if the left-hand seat pilot commands full down with his side stick, while the right-hand seat pilot at the same time commands full up, The end result is that the aircraft actually fails to react at all, as both inputs cancel each other out, obviously a less than ideal situation. Hence Airbus have installed a warning system to alert pilots by both visual and oral means anytime both side sticks are moved at the same time from the neutral position by more than 2 degrees. In such circumstances, a warning light will illuminate on the glare shield in front of each pilot and an associated oral warning will be generated.
Dual input.
If either pilot wishes to take exclusive control of the aircraft and physically remove the other from the equation, the red autopilot disconnect takeover push button must be pushed and held. In the example shown, the captain is seen fit to take control. This could be for reasons of incapacitation or perhaps on witnessing inappropriate control inputs from the first officer. As the takeover push button is depressed, a red arrow illuminates on the glare shield in front of the FO, pointing in the direction of the captain, and an oral warning is simultaneously triggered.
Priority left.
If the first officer persists with movement of his side stick while it is deactivated, the green side stick priority light will illuminate in front of the captain to highlight this fact. Had the example shown the first officers being the pilot wishing to take control, the oral and visual indications would obviously have been reversed. In the example shown, if the captain's takeover push button is released within 40 seconds, the first officer's inoperative side stick becomes live once again. If it is held for more than 40 seconds, the first officer's side stick will remain disabled for however long, until such time as its takeover push button is pressed, at which time normal operation will be resumed. A flight director system is an instrument system consisting of electronic components that compute and indicate the aircraft's attitude required to attain and maintain a pre-selected flight condition. These pre-selections of pitch and roll are made by way of selections on the FCU, positioned on the glare shield between both crew members. Displayed by means of a dedicated on-off switch, one for each pilot. Once selected on, command bars on the respective primary flight display shows the pilot how much and in what direction the attitude of the aircraft must be changed to achieve the desired result. The flight director incorporated on the A330 comprises of 2 green bars forming a crosshair. The horizontal bar will provide the pilot with pitch guidance to the selected target, while the vertical bar will provide roll guidance. The computed command indications relieve the pilot of many of the mental calculations required for instrument flights, such as interception angles, wind drift correction, and rates of climb and descent. Thus they are used almost continuously, providing an extremely strong visual connection between pilot input and resultant aircraft behaviour. By way of example as to how the flight directors will appear to the pilot, have a look at the following examples. The aircraft's orientation is represented by the airplane symbol mid-screen. In the diagram to the left of screen, the FMA is indicating alt cruise. What this means is that the flight director pitch guidance is for the pilot to maintain the target altitude, which in this case will be 15,000 feet. However, the aircraft is not flying level, but rather descending through about 14,300 feet at a rate of 5,900 feet per minute. As a result, in order to correct the situation and return to the target altitude of 15,000 feet, the pitch bar of the flight director is instructing the pilot to raise the nose of the aircraft or to pitch up. This descending turn is also taking the aircraft away from its assigned heading, which is indicated here as 300 degrees. Therefore, in the context of roll, the flight director roll bar is providing guidance to simultaneously turn left to reacquire the target heading. With regard to the second example on the right, here the aircraft has deviated above the target altitude and drifted off the assigned heading to the left. As a result, to reacquire the assigned altitude and heading, the flight director bars are commanding a pitch down and simultaneous turn to the right. Why these flight directors are important in the context of 447 is that by design, when the aircraft is flown intentionally or otherwise to extremes of pitch or roll, the flight directors are automatically removed from view. The logic here is that removing the flight directors in such extreme attitudes allows the pilot to concentrate solely on correcting the abnormal state without the distraction of flight director commands, which are most likely irrelevant under the circumstances. Provided they are not switched off in the interim, as the aircraft is returned to more normal attitudes, the flight directors will reappear. However, as was the case prior to this accident, when they reappear, they do so in the basic modes of heading vertical speed, irrespective of what modes they were in previously, and they adopt the aircraft's current trajectory values of pitch and roll as the new guidance values. By way of example, assume the aircraft was navigating direct to a navigation beacon and maintaining level flight. The flight director would be centered, forming a cross on the PFD, centered on the aircraft symbol, providing no pitch or roll corrections, as none were necessary with the aircraft navigating as it should. Subsequently, the aircraft experiences an upset. This could be due to environmental or technical issues, or perhaps even triggered by mishandling on the part of the pilot. Regardless, the aircraft banks hard to the right. Assuming the bank angle exceeds 45 degrees, the flight directors will be removed from view. As the aircraft recovers and the bank angle is reduced below 40 degrees, the flight directors will reappear. However, when they reappear, they will show guidance to maintain both the aircraft's current heading and vertical speed. In other words, no longer are the flight directors providing guidance to the initial navigation aid while maintaining level flight. Now they command the pilot to maintain the current aircraft heading and the instantaneous rate of climb or descent which existed at the moment they reappeared. In the case of 447, the instantaneous vertical speed adopted by the flight directors as they reappeared directed the pilots to maintain a rate of climb which was completely inappropriate given their increasing angle of attack. Following the accident, the BEA made a recommendation that such flight director behaviour be modified, that in future, on their reappearance, the flight directors would re-engage on the original modes, thus continuing to provide valuable information to the pilot on how to recover back to the initial trajectory. This recommendation was subsequently accepted and implemented by Airbus, so that all 330s and 320s for that matter worldwide now operate to a safer code of practice. Normal law is the default control law, and consequently this is where the aircraft operates for the vast portion of any given flight. The only time the aircraft moves outside of this control law is either by design in order to execute the takeoff and landing maneuvers, in which case the laws are deliberately modified slightly, or subject to some in-flight technical malfunction, the consequences of which will no longer facilitate the application of normal law, and the aircraft control laws are subsequently downgraded. In the context of pitch in normal law, the aircraft responds to side-stick forward and aft inputs in order to generate a G-load pitch rate response, where a pitch-up demand at high speed will generate a high vertical acceleration or G-load for a modest actual pitching rate. The converse is true at low speed, where a given pitch input produces a lesser vertical acceleration or G-load proportional to the actual pitch rate. For this reason, when we talk of pitch commands in normal law, we're actually talking of a blended pitch rate and G-loading output to satisfy flight control input demands being made by the pilot. Normal law incorporates automatic pitch trim. When the pilot makes a pitch input through the side stick, the flight control computers command the pitch with elevator, then automatically trim the horizontal stabilizer in order to keep the elevator in an average neutral position. Were this not to be the case and the aerodynamic loading was to be held by the elevator alone, any subsequent request made of elevator travel may in fact not be possible, with the obvious disastrous implications this would have for safe manoeuvrability of the aircraft. The trim action happens in the background without any conscious consideration on the pilot's part. On the 330, when a pitch input is made and the side stick released, this target pitch attitude is prioritised and tends to remain the same. Thus, the aircraft exhibits pitch stability at the expense of speed stability. This is significant with regard to our further examination of 447. Remember, in a conventional aircraft, if the situation were to develop whereby the aircraft was placed in a climb with insufficient thrust to maintain the desired trajectory, the resultant speed loss would cause the nose of the aircraft to lower or pitch down in order to maintain the in-trim speed. Again, in normal law, this will not occur. Maintaining the flight trajectory through pitch will be the priority. If we lose speed in the process and our angle of attack increases towards concerning levels, the built-in protections which normal law facilitates will ultimately be activated, mitigating the possibility of aerodynamic stall. So what are these protections? As I mentioned earlier, one of the advantages of a fly-by-wire system which utilises computers to position the aircraft's control surfaces, be that elevators, ailerons, flaps, spoilers, etc., is that the computers can be instructed to intervene if the side stick demand from the pilot has the potential to damage the aircraft or take it outside of its normal operating envelope, a stall for example. Essentially, there are 4 pitch protections and 1 roll protection as follows. Maneuver protection, which prevents structural overstressing of the airframe. Pitch attitude protection, which limits the physical pitch attitudes the pilot can achieve through the side stick to a maximum of 30 degrees nose up, 15 degrees nose down. Over bank protection, ensuring bank angle limitation of 67 degrees. High speed protection, and most important in the context of 447, high angle of attack protection. This specific protection is designed to prevent the aircraft from stalling and to ensure optimum performance in extreme manoeuvres such as wind shear or ground proximity warning system recovery. This protection takes priority over all others. Angle of attack is the angle formed by the chord of the airfoil and the direction of the relative wind, or the vector representing the relative motion between the aircraft and the atmosphere. In simplified terms, it can be described as the difference between where the wing is pointing and where it's going. Why it is important and why have it protected? Well, as the angle of attack is increased, the lift produced by the wing will also increase, up to a point. This point is called the critical angle of attack. Beyond this value, the airflow can no longer follow the curvature of the airfoil and begins to separate. Lift is lost and the aircraft is said to have stalled. With no angle of attack indicator on the 330 cockpit, this protection, although triggered by an increasing angle of attack, manifests itself to the pilots through the speed tape on the primary flight display. As speed decreases, it reaches VLS, lowest achievable speed with auto thrust engaged. This is indicated as the top of the hollow amber bar at the lower end of the speed tape. Auto thrust, if engaged, will apply engine power to stop any deceleration below this value in order to limit the angle of attack being flown. With auto thrust inoperative or not engaged, the speed can reduce to the first level of angle of attack protection, V alpha prot, which is shown as the top of the amber and black band. At this indicated airspeed, the actual angle of attack which has been reached will trigger the high angle of attack protections. The autopilot, if engaged, will disengage, and the flight control computers will lower the nose in order to maintain a maximum angle of attack equivalent to V alpha prot. And with the side stick in the neutral position, any bank on at the time will be removed and the aircraft rolled wings level. The maximum bank angle achievable will also be reduced from 67 degrees to 45 degrees in order to mitigate potential G-loading of the aircraft, which could act to exacerbate the already high angle of attack condition. For whatever reason, should the pilot decide to resist this effort to maintain an angle of attack at V alpha prot and continue to apply back pressure on the side stick, the speed can further reduce to V alpha max, represented on the speed tape as the top of the solid red band. Close inspection of the graph to the left will show the correlation between airspeed and angle of attack. As can be seen, V alpha max will correspond to an angle of attack just shy of CL max, the critical value beyond which the wing will stall. If the pilot subsequently does release back pressure on the side stick, the protections will again persist with pitching the nose down to the extent that angle of attack is reduced to the value equivalent to V alpha prot. In normal law, the flight control computers will maintain V alpha max, even if the pilot holds the side stick fully aft. Nose up pitch trim is inhibited. In this protection range, the normal law demand is modified, and side stick input is an angle of attack demand instead of a load factor demand, as was previously the case for pitch commands in normal law. In reality, provided the autothrust is serviceable, the speed is unlikely to actually reduce to V alpha max before the alpha floor protection is triggered. In this instance, the aircraft applies maximum engine thrust and holds the angle of attack at a maximum of V alpha max. Once activated, the pilot can exit alpha floor only by significantly reducing the angle of attack with forward pressure on the side stick. A single system failure would not result in the loss of normal law. However, multiple failures of flight controls, hydraulics, or electrical system components may result in degradation. The level of degradation will depend on the severity of the failure. Usually, however, where degradation occurs, the downgrade is from normal to alternate law. Along the longitudinal axis, load factor demand remains the same as normal law. In other words, despite any possible degradation, in pitch the aircraft behaves the same regardless of whether it's in normal or alternate law. Along the lateral axis, that is in roll, things however are somewhat different depending on which subsection we find ourselves in. In alternate law 1, roll command remains a rate of roll command similar to normal law. In alternate law 2, however, roll control is conventional in nature, insofar as flight control surface deflection is proportional to side stick deflection. That being the case, roll sensitivity is proportional to airspeed, with the feel to the pilot being a lot more sensitive. Around the yaw axis, damping is available, be it with limited authority. Significantly, however, whether the aircraft has been downgraded to alternate law 1 or 2 isn't apparent to the crew. In alternate law, most of the protections we have come to take for granted in normal law have been lost. However, in most circumstances, these have been replaced with stabilities. In normal law, if the pilot's intention is to fly the aircraft deliberately outside the normal flight envelope, the flight control computer simply won't allow it. With alternate law stabilities, however, the flight control computers, although still sensing impending danger, will only act to suggest that this course of action is inappropriate. They will make modest efforts to restrict pilot actions, but where the pilot remains determined in his efforts, he will be able to drive through these stabilities and do with the aircraft what he wishes, even if this does take the aircraft outside of the normal operating envelope. The following example illustrates the point. In the case of a high angle of attack protection, we've already reviewed how the aircraft will behave in normal law. In alternate law, the situation is somewhat different. You'll notice from the slide that once the reconfiguration has occurred, the symbology on the speed tape physically changes. Now that we are in alternate law, gone is the black and amber bar representing alpha prot. An alpha max solid red bar indication has been replaced with the black and red barber's pole representing VSW, or the point at which the stall warning alert will be triggered. As speed approaches VSW, a gentle, progressive nose-down pitch input is introduced to lower the nose and prevent further speed loss. This is the stability in action. However, if the pilot is of the mind to do so, this nose-down input can be overridden, resulting in the aircraft being flown into the stall. Importantly for our further examination of 447, where aircraft weight, flap position data, or dual or triple air data loss or disagreement occurs, essentially meaning invalid speed senses, these load speed stabilities are rendered useless and are simply not available. Such is largely the case when the aircraft enters alternate law 2. In the context of Air France 447, the environmental conditions the aircraft will encounter will severely impact on the aircraft's ability to compute an accurate airspeed using the onboard air data reference units, or ADRs. With 3 ADRs fitted to the aircraft, if one source diverges greatly from the other two, it is voted out or rejected by the PRIM, the primary flight control computer. In such circumstances, with 2 sources of data remaining, the flight control laws will remain in normal law. However, As will be the case with 447, if the remaining two data sources themselves begin to diverge from each other, the aircraft becomes completely unsure of its actual speed, as it sees no individual source as being truly correct. The prims will subsequently reject both remaining sources of information, and the flight control laws will be reconfigured to alternate law 2. Furthermore, the rate at which the indicated airspeeds in the cockpit diverge away from the average figure of the data source is in itself a consideration for reconfiguration. A loss of indicated airspeed of more than 30 knots within 1 second time frame will also initiate reconfiguration to alternate law 2 and cause the subsequent disconnection of the autopilot. This is exactly what will happen to 447. Direct law and mechanical backup are further degradations of the control laws, but having no relevance to our study of 447, these have been overlooked here. An important aspect of understanding the individual events of this particular accident is an insight into how the aircraft communicates technical defects to the crew. Pretty much all aircraft, some level of warning is used to grab the pilot's attention, be that visually, hourly, or more commonly both, and in this regard the 330 is no different. Essentially, the warning and alerting system centres around two electronic boxes called the System Data Acquisition Concentrators, or the SDACs. These units monitor in real time all the various systems of the aircraft. If they detect an anomaly, or worse, a defect of any sort, they immediately forward that information to a pair of flight warning computers for immediate generation of appropriate visual and aural alerts. These visual alerts are displayed in both pilots' line of sight by respective red warning or amber caution lights on the glare shield. Accompanying aural alerts are simultaneously broadcast through the cockpit loudspeakers, left and right side. Further, the SDACs also send this warning information to the respective display management computers, or DMCs, which visually identify the failure and its associated checklist response on the upper or engine warning display screen, while at the same time, if applicable, also depict the affected system in diagrammatic form on the lower or the system display screen. The system in its entirety is called ECAM, Electronic Centralized Aircraft Monitor. Airbus rely heavily on colour to impart information to the pilot. In the context of error or failure messaging, red indicates that the failure is of the highest priority, referred to as a level 3 warning, and that corrective action must be applied immediately. On activation of a level 3 warning, the glare shield attention getters will flash red while a continuous repetitive chime is heard in the cockpit until acknowledged and silenced by the crew. On the EWD, the nature of the warning is displayed. In this instance, a number 1 engine fire, with the appropriate checklist items requiring action by the crew being displayed below in blue. As the crew action each item on the checklist, the associated line is automatically removed. Once all the lines have been removed, the checklist is deemed to have been completed. Of a lesser priority are the level 2 cautions. These items, being of lesser importance, are displayed in amber, and by definition, although still important, need not be addressed with the same haste as the level 3 warning. On activation of a level 2 caution, the glare shield attention getters will illuminate steady amber, while a single chime will be heard in the cockpit. On the EWD, the nature of the warning is displayed. In this instance, a number 1 engine pneumatic bleed leak. Once more, the appropriate checklist items requiring action by the crew are displayed below in blue. As the crew action each item on the checklist, as before, the associated line is automatically removed. The lowest of all cautions is the level 1 caution. Being of least importance when displayed, unlike the previous level 2 caution, these level 1 cautions will not generate any visual or aural warnings for the crew. Another obvious difference between these and the previous level 2 cautions is that they have no associated action items. Indeed, the Flight Crew Operations Manual simply states that the only subsequent crew action is awareness. The example on screen shows a typical Level 1 caution associated with a digital flight data recorder fault. The level below these cautions is referred to as the advisories, as they have no significance in explaining the events surrounding Air France 447. For the sake of brevity, I've chosen to overlook them here. What is, however, extremely relevant is an understanding of how ECAM prioritises the failures that it reports. If we go back for a second to the previous example of the Level 3 warning concerning the engine 1 fire, if while working through the checklist ECAM actions, the system detects a further failure, the DFDR for example, as this new failure is only a Level 1 caution, ECAM will place it below the Level 3 warning for attention by the crew once the failure of higher priority has been addressed. As we continue with our execution of the checklist, suppose the autopilot was to be inadvertently disengaged. Autopilot failure or inadvertent disengagement is classified as a Level 3 warning. Indeed, so is the engine fire. However, on the assumption that the crew do not wish to impact the ground while executing the engine fire drill, the autopilot disengagement is now reclassified as the most important issue for the crew to address. This very situation, however, highlights some of the potentially more complex aspects of working one's way through the ECAM display. For example, where's the FDR fault now? It was in view only a few seconds ago prior to autopilot disengagement. Well, it's still there, just not visible at the moment, because the physical dimensions of the lower part of the EWD will only facilitate 7 lines of text. Prioritization of the autopilot off message has bumped the DFDR fault into the overflow section. The newly appeared green arrow at the bottom of the page draws the pilot's attention to this very fact, and the title of the failed system, namely recorder, being queued on the lower right hand side of the screen, also indicates that as the drill is completed and lines are systematically removed from the screen, the free space this will create will be filled in time once again by the recorder DFDR fault message.
Every day, thousands of Airbus aircraft take off and land all over the world, in total safety for passengers, freight, and of course the crews. However, because not all flights are ever quite the same, unexpected and rare events may happen, requiring a calm recovery reaction from the crew. The stall is one of these unexpected events. Here the crew must fully understand what is going on to be able to adapt and control the situation, with one sole aim: recover the aircraft. So it is possible to recover an Airbus from a stall situation. Over and above the currently published documents that resulted from collaborative work between aircraft manufacturers and air safety organizations, we would like to go further in explaining the characteristics of the stall phenomenon, and specifically how to recover from a stall. For all pilots, the top priority is to clearly identify an approaching stall, so that the stall itself can be avoided. However, should one be encountered, then the correct recovery actions must be taken immediately. A stall is characterized by a loss of control, then by a loss of height. A wing generates lift, where L equals a half rho v squared SCL. The lift must equal the weight of the aircraft times the load factor. L equals N times W. N equals load factor, W equals weight. The general lift equation becomes N times W equals L equals a half rho v squared SCL. The CL of the wing increases with the angle of attack up to a maximum CL max. Any further increase of angle of attack above this angle of attack of CL max will make it impossible for the airflow to smoothly follow the upper wing surface. The flow will separate from the surface, causing the CL to decrease and drag to increase. On this graph, we can clearly see that the angle of attack increases from zero lift value. The curve is linear over a big range. When the flow separation begins, the slope of the curve begins to fall off. The lift reaches a maximum and begins to decrease. The angle of attack at which it starts to decrease is the stalling angle of attack or critical angle of attack. This corresponds to the value of CL max. One can clearly notice that to recover from a stall or to prevent a stall, the angle of attack must be decreased to below this CL max value. The aircraft is considered stalled when the behavior of the aircraft gives the pilot a clear and distinctive indication that the aircraft is stalled. Indications of a stall, occurring either individually or in a combination, are a nose-down pitch that cannot be readily arrested, buffeting of a magnitude and severity that it becomes a strong and effective deterrent to further speed reduction. The pitch control reaches the aft stop, and it is impossible to stop the aircraft from descending. Stall characteristics vary with different types of aircraft. However, for modern aircraft during most normal maneuvers, the onset of the stall is gradual. The first indications of an approaching stall may be provided by any or all of the following: unresponsive flight controls, a stall warning or stall prevention device, significant uncommanded roll at the stall, or aerodynamic buffeting. The transition from approaching stall to stall is sometimes difficult to identify precisely. Therefore, the two phases should be treated as the same from a recovery point of view. Factors that affect the stall speed are change in weight, maneuvering the aircraft increasing the load factor, configuration changes. This is how the CL versus angle of attack changes with slats extension, flaps extension, speed brakes extension, and finally wing contamination. Let's see how the CL max varies with the Mach. Remember the general lift equation, N times W equals L equals a half rho V squared SCL. Expressed in Mach condition, it becomes N times W equals L equals 0.7 P Mach squared SCL. At a low Mach number for a given configuration, a wing stalls at a given angle of attack. Beyond a given Mach number, order of magnitude Mach 0.35, any Mach number increase has two consequences. The angle of attack at which the wing stalls decreases. The maximum lift coefficient, which is obtained at stall angle of attack, decreases as well. It means that at high altitude, where Mach effects become significant, the margin from the stall decreases. In other words, in a high-altitude cruise, when the Mach number increases, the lift capacity decreases. That is to say, the load factor capability decreases, as does the ability to maneuver. That being said, let's now take a look at particular stall phenomena. Accelerated stall. An accelerated stall is caused by abrupt or excessive control movement. An accelerated stall can occur during a sudden change in flight path, during maneuvers such as steep turns or a rapid recovery from a dive. It is called accelerated stall because it occurs at a load factor greater than 1g. Secondary stall. A secondary stall may be triggered while attempting to recover from a stall. This usually happens as a result of trying to hasten the stall recovery, either by not decreasing the angle of attack enough at stall recognition stall warning, or by not allowing sufficient time for the aircraft to begin flying again before attempting to regain altitude loss. Pitch up effect. The shape of the wing will also determine the stall characteristics. Modern jet aircraft have swept back wings. This kind of wing allows higher speed, but it has an increased tendency to stall at or near the wingtip first. The loss of lift at the wingtip moves the center of pressure forward, thus inducing a pitch-up moment. So, what do we have to remember? For a given Mach number, a wing stalls at a given angle of attack. When the Mach number increases, the value of angle of attack stall decreases. When approaching the angle of attack stall, the wing generates a certain level of buffeting, which tends to increase at a high Mach number. When the angle of attack increases and approaches the angle of attack stall, in certain cases, a phenomenon of pitch up occurs as a result of the change in lift distribution on the wing. When the flow over the wing is stalled, the only possible means to recover a normal flow is to decrease the angle of attack to a value lower than the angle of attack stall. Stall is only an angle of attack problem. It is not directly a speed problem. Remember these last 2 points. So, that's the theory. But how does it work in practice? For this, we've decided to use a production A330, representative of aircraft in service. Let's start with deterrent buffet. Deterrent buffet is a phenomenon which happens at a certain stage in a stall. It is so strong that it can be dissuasive. It should be noted that the definition of deterrent buffet is part of the stall definition as specified in documents certified by the civil aviation authorities. Buffeting starts gently and gradually increases until the pilots decide to recover. Note that buffeting is hardly perceptible at all when the warning is triggered, but builds up quite quickly to a very harsh level.
Stall, stall. Stall, stall. Stall, stall. Stall, stall. Stall, stall.
Let's focus now on the recovery. In this shot, we have inserted a cross symbol to represent the stick. When the stick is pulled backwards, the cross moves to the nose up position. When the stick is pushed forwards, the cross moves to the nose down position. You can now observe that during the whole recovery, we made a nose down input. We can therefore deduce that deterrent buffet is directly associated with the turbulent airflow, wing stalled condition, and that it disappears when the stick is pushed forward and the flow reattaches. In this graph, you can see the angle of attack at which the stall warning will start in function of the Mach number. You can note that the stall warning angle of attack decreases as the Mach increases. There is also the curve showing the buffet onset. The zone above the stall curve is the deterrent buffet zone. You can see that as the angle of attack increases, we enter the different zones on the graph. Once the recovery is initiated, this deterrent buffet stops. You may also notice that the sudden change in angle of attack occurs as soon as the recovery procedure is applied. Let's review this again. In the event of a significant uncommanded roll at the stall, reduce angle of attack before recovering the bank angle. In this film, you have seen various theoretical and practical aspects of stall situations. The most important thing to remember is that, at the first indication of a stall, you must release the back pressure and, if necessary, push the stick forward to decrease the angle of attack until the stall indications are no longer present. Remember, it is always better to avoid a stall, but should you encounter one, strictly apply the recovery procedures published in your aircraft operations manual.